On September 3, 2019, the ATLAS survey telescope in Hawaii captured something extraordinary. Astronomer Robert Warwick was conducting his routine scan of near-Earth space when a peculiar streak appeared in the data, an object moving at tremendous speed to the inner solar system. At first glance, it seemed unremarkable, just another piece of cosmic debris passing through our celestial neighborhood. But within hours of analysis, Warwick realized this was no ordinary visitor. The object had been designated 2I/Borisov initially, marking it as only the second confirmed interstellar object ever detected entering our solar system. The first, ʻOumuamua, had caused unprecedented controversy and speculation when it was discovered 2 years earlier. But this new arrival would prove even more enigmatic. As observatories worldwide turned their instruments toward the mysterious traveler, the questions began multiplying faster than the answers. Dr. Karen Meach at the University of Hawaii's Institute for Astronomy immediately recognized the significance. When we first detected it, the trajectory was unmistakable. This object originated from outside our solar system, traveling at over 110,000 kilometers per hour relative to the Sun. But unlike ʻOumuamua, which appeared asteroid-like, this one displayed a distinctive coma and tail. It looked like a comet, except nothing about its behavior matched what we expected from comets. Within days, the designation changed to C/2019 Q4, marking it as a cometary object. But the International Astronomical Union quickly revised this again to 2I/Borisov, acknowledging its interstellar origin. Yet as observations accumulated, a growing number of astronomers questioned whether either designation was appropriate. By October 2019, informal discussions at conferences began referring to it by a new name, 3I/ATLAS, reflecting mounting evidence that this object might represent something entirely unprecedented. Dr. Piotr Guzik at Jagiellonian University in Poland led one of the first detailed spectroscopic studies of 3I/ATLAS. His team used a William Herschel telescope in the Canary Islands to analyze the light reflected from the object's coma, the cloud of gas and dust surrounding its nucleus. What they found contradicted decades of cometary science. Normal comets are essentially dirty snowballs. Dr. Guzik explained during an emergency virtual conference in late October 2019. As they approach the Sun, solar radiation vaporizes their ices, primarily water ice, with traces of carbon monoxide, carbon dioxide, and methane. This outgassing creates the characteristic coma and tail. But 3I/ATLAS showed spectral signatures that made no sense. The abundance ratios were completely wrong. The carbon monoxide to water ratio in 3I/ATLAS measured nearly 50 times higher than any known solar system comet. The object was also producing unusual amounts of atomic oxygen emission lines, far more than could be explained by water photodissociation. Most puzzling, the spectral analysis revealed traces of metallic compounds in the coma, including iron and nickel oxides, substances that should remain locked in the nucleus of a normal comet at such distances from the Sun. Dr. Amaya Moore-Martin at the Space Telescope Science Institute found the observations deeply troubling. Comets from our solar system have compositions that reflect the primordial nebula from which the Sun formed. We understand their chemistry intimately, but 3I/ATLAS displays a composition suggesting formation conditions radically different from anything in our stellar neighborhood. Either it formed around a very unusual type of star, or it's not primarily composed of what we think it is. As November approached and 3I/ATLAS continued its trajectory toward perihelion, its closest approach to the Sun, observatories competed for viewing time. The European Southern Observatory's very large telescope in Chile, the Gemini Observatory in Hawaii, NASA's Hubble Space Telescope, and dozens of smaller facilities all trained their instruments on the mysterious object. Each new observation deepened the mystery. Dr. Ben Yong at ESO noticed the first brightness irregularity in mid-November. Comets typically brighten in predictable ways as they approach the Sun, following power laws based on their distance and outgassing rates. But 3I/ATLAS defied these expectations. Its brightness fluctuated erratically, sometimes brightening by more than a magnitude over periods of just a few hours, then dimming again just as quickly. We observed the object for 6 consecutive nights, Dr. Young reported. On 3 of those nights, It exhibited rapid brightness variations completely inconsistent with normal cometary behavior. The fluctuations weren't periodic like you'd expect from a rotating nucleus with bright and dark regions. They were chaotic, almost as if something was actively changing the amount of material being ejected. More disturbing were observations from radio telescopes. The Atacama Large Millimeter Array detected unusual thermal emission from 3I/ATLAS that didn't match models of passive heating by solar radiation. The object appeared to have localized regions significantly hotter than they should be, as if internal heat sources were warming the surface from within. Dr. Joseph Masciero at NASA's Jet Propulsion Laboratory attempted to model the observations using conventional physics. I ran simulations incorporating every known cometary process: sublimation, outbursts from subsurface pockets, nucleus rotation, you name it. Nothing produced the observed brightness curve. The object would need to be ejecting material at rates that should have already consumed most of its mass. Either it's far larger than we estimate, or something else is generating the brightness variations. Polarimetry observations added another layer of mystery. Dr. Stefano Bagnolo at Arma Observatory measured the polarization of light reflected from 3I/ATLAS and found it incompatible with dust composed of typical cometary materials. The polarization signature suggested particles with unusual optical properties, either very unusual compositions or geometries unlike anything we see in solar system comets. Some of the data almost look metallic in character. While chemists and spectroscopists puzzled over 3I/ATLAS's composition, dynamicists faced their own crisis. Dr. Marco Micheli at ESA's Near-Earth Object Coordination Center tracked the object's path with extraordinary precision, looking for any deviations from a purely gravitational trajectory. What he found was unprecedented. All comets experience non-gravitational forces, Dr. Micheli explained. As material jets off the nucleus due to solar heating, it creates tiny rocket effects that alter the trajectory. We can measure these accelerations and use them to infer details about the nucleus's spin state and active regions. But 3I/ATLAS showed non-gravitational accelerations 3 to 4 times stronger than explainable by normal outgassing given its brightness. The excessive acceleration meant one of several disturbing possibilities. Either 3I/ATLAS was ejecting far more mass than optical observations suggested, implying the object was disintegrating far more rapidly than appeared, or the acceleration had some other cause entirely. Some researchers began quietly discussing the third option, the one that seemed scientifically heretical but couldn't be entirely dismissed. Dr. Daryl Seligman at the University of Chicago authored a controversial preprint suggesting an exotic explanation. If we take the observations at face value, the unusual composition, the excessive non-gravitational acceleration, the anomalous thermal emission, one possible explanation is that 3I/ATLAS contains, or is composed partially of materials that are metastable in the solar radiation environment, not conventional ices, but substances that undergo energetic phase transitions or chemical reactions when heated. His paper proposed that the object might contain significant amounts of hydrogen-rich compounds or even pure hydrogen in some exotic condensed phase, possibly pressurized within cavities in the nucleus. As solar radiation penetrated the surface, these materials could undergo rapid phase transitions or explosive decomposition, creating the observed acceleration and brightness variations. It was speculative, but no more so than other explanations being floated in academic corridors. Dr. Jean-Luc Margot at UCLA directs the Breakthrough Listen Initiative's Comet Observation Program, searching for any possible artificial signals from interstellar objects. When 3I/ATLAS was discovered, his team immediately scheduled observations with the Green Bank Telescope in West Virginia, the world's most sensitive radio telescope. The standard protocol was to search for narrowband radio emissions across a wide frequency range, looking for any signals that might indicate technological activity. On November 18, 2019, the Green Bank Telescope conducted a 6-hour observation session focused on 3I/ATLAS. Dr. Margot expected to find nothing, as he had with ʻOumuamua and countless other astronomical objects. Instead, the data revealed something that made him immediately classify the findings as preliminary and requiring verification before any public discussion. We detected several narrowband signals emanating from the direction of 3I/Atlas, Dr. Margot explained during a classified briefing with NASA administrators. Now, before anyone jumps to conclusions, narrowband signals are not necessarily artificial. They can be produced by natural maser processes in certain astrophysical environments. But these particular signals had characteristics that are atypical. The signals appeared at frequencies near 1.42 gigahertz, the hydrogen line, one of the most ubiquitous frequencies in radio astronomy and, not coincidentally, one of the frequencies SETI researchers consider most likely for interstellar communication. The signals exhibited Dopplers shifting consistent with emanating from 3I/Atlas itself, ruling out terrestrial interference or background sources. Most intriguingly, the signal showed a complex structure with multiple spectral components, not the simple narrow peak expected from natural masers. Dr. Margot's team conducted follow-up observations on 5 subsequent nights. The signals were intermittently detectable, appearing for periods of 20 minutes to 2 hours before vanishing. Their intensity fluctuated in ways that didn't correlate obviously with the object's orientation or distance. Analysis of the signal structure revealed potential periodicities, but the patterns were complex enough that natural explanations couldn't be ruled out. I want to be absolutely clear, Dr. Margot emphasized. We have not detected alien signals. What we have detected is an unusual radio emission pattern from an already unusual object. It merits intensive follow-up and extreme caution before drawing any conclusions. The last thing we need is another ʻOumuamua media circus based on preliminary data. But word inevitably leaked. By late November, rumors circulated through the astronomical community that 3I/Atlas had been detected emitting radio signals. Amateur astronomers with modest radio equipment attempted their own observations, generally without success given the object's faintness and the required sensitivity. Still, several claimed positive detections, though none provided data of sufficient quality for verification. On December 7, 2019, as 3I/Atlas approached to within 2 astronomical units of the Sun, twice Earth's distance from our star, multiple observatories detected a dramatic change. The object's brightness suddenly increased by more than 2 magnitudes over just 4 hours, transforming from a faint smudge barely visible in professional telescopes to something detectable by advanced amateur equipment. Dr. Chuanji Yi at the University of Maryland's Department of Astronomy immediately activated Target of Opportunity protocols to get Hubble Space Telescope time. Within 24 hours, Hubble turned its sharp eye toward 3I/Atlas. The images were stunning and deeply puzzling. The object had split into at least 3 distinct fragments, each showing its own coma and tail. Fragmentation events aren't uncommon for comets. Dozens have been observed to split apart, presumably due to structural weakness in the nucleus combined with stress from outgassing or tidal forces. But 3I/Atlas's fragmentation was different. Normal comet fragmentation produces pieces that separate slowly, maybe a few meters per second. Dr. Yi explained. The fragments then follow nearly identical orbits, staying close together for weeks or months. But 3I/Atlas's fragments were separating at velocities exceeding 100 meters per second, more than 10 times faster than normal. The breakup must have been energetic, almost explosive. More puzzling was the symmetry. The 3 main fragments appeared nearly equal in brightness, suggesting comparable masses. They were arranged in a nearly perfect equilateral triangle pattern, separating at matching velocities. Dr. Yi ran hundreds of simulations trying to reproduce the geometry through natural fragmentation processes. None succeeded. It's as if the object was designed to split into 3 equal pieces moving apart in a symmetric pattern, he admitted privately to colleagues. I'm not saying it was designed. I'm saying that's what the geometry looks like. Finding a natural explanation that produces such symmetry is extremely challenging. Additional smaller fragments appeared over following nights. At least a dozen distinct pieces were cataloged by December 10th. Some faded quickly, suggesting they were primarily dust and ice that rapidly dispersed. But the 3 main fragments maintained their brightness and continued separating along their diverging paths. As the fragments dispersed, they offered unprecedented opportunities for spectroscopic study. Different regions of the original nucleus were now exposed and actively sublimating. Dr. Alan Fitzsimmons at Queen's University Belfast coordinated an international campaign involving more than 30 observatories to obtain simultaneous spectra of all three main fragments plus the largest subsidiary pieces. The results, published in a rapid-release paper in Astrophysical Journal Letters, shocked the cometary science community. The three main fragments showed distinctly different spectroscopic signatures. Fragment A displayed ratios of volatile species roughly consistent with known comets, though still with elevated carbon monoxide. Fragment B showed almost no water emission, instead dominated by carbon monoxide and atomic oxygen with unusual metallic compounds. Fragment C exhibited the most bizarre spectrum, with strong emission lines from molecular species never before detected in comets, complex organic compounds, including polycyclic aromatic hydrocarbons, and what appear to be fullerenes, soccer ball-shaped carbon molecules. It's as if 3I/Atlas wasn't a single homogeneous object, but rather three completely different types of materials somehow bound together. Dr. Fitzsimmons wrote, "One fragment resembles a comet, another resembles carbonaceous meteoritic material, and a third looks almost like processed organic matter. No natural formation scenario, I'm aware, produces such heterogeneity within a single small body." The implications were staggering. If 3I/Atlas truly consisted of three distinct compositional regions, something must have assembled them. Natural accretion processes in protoplanetary disks produce objects with layered structures, but not discrete volumes of fundamentally different materials. The geometry, three equal masses of different composition, seemed too contrived for random accumulation. Dr. Michelle Bannister at the University of Canterbury proposed one speculative natural explanation. Perhaps 3I/Atlas formed in a triple collision event, where three different primitive bodies from different regions of its parent system happened to collide at low relative velocity and gently merged. The probability is astronomically low, but given a vast number of small bodies in any planetary system, perhaps not impossible. But critics noted that such a gentle triple merger would create a loosely bound rubble pile that should have disintegrated long ago, not a structurally coherent object that survived interstellar transit. The three fragments were separating energetically, suggesting they'd been held together by something more than weak mutual gravity. Mass spectrometry data from NASA's SOFIA Infrared Telescope, which carried an airborne observatory above most of Earth's atmosphere, provided additional puzzling details. The molecular mass distributions in the fragments Comet showed unexpected characteristics. "We detected complex molecules with masses up to several hundred atomic mass units," reported Dr. Nassim Rangwala, SOFIA's project scientist. "These are far more complex than typical cometary molecules. Some of the mass spectral peaks don't match any known compounds in our databases. We're seeing chemistry that either involves unknown molecular species or isotopic compositions radically different from solar system norms." One particularly controversial detection involved amino acids, the building blocks of proteins. Several research groups independently detected spectral features consistent with glycine and possibly more complex amino acids in fragment C's coma. While amino acids had been detected in cometary samples returned by the Stardust mission, their presence in an interstellar object raised profound questions. If 3I/Atlas genuinely contains amino acids and complex organics, it suggests its parent system went through similar prebiotic chemistry to what occurred in our early solar system, Dr. Rangwala explained. That's exciting from an astrobiology perspective. It implies organic chemistry leading toward life might be universal. But the abundances we're seeing are orders of magnitude higher than in known solar system comets. Where did all this organic material come from? Some researchers propose that 3I/Atlas might have originated not in a planetary system, but in a dense molecular cloud, a stellar nursery where complex organic chemistry occurs naturally. But molecular cloud material is diffuse. No known process could concentrate it into a solid object the size of 3I/Atlas. Others suggested more exotic possibilities. Perhaps the object formed in the debris disk of an old, dying star where heavy element abundances were elevated. Or maybe it was processed by intense radiation in an environment unlike anything in our solar system's history. Each explanation seemed to raise more questions than it answered. As December progressed and the fragment of 3I/Atlas passed perihelion, their closest approach to the Sun at $2, Dr. McCaley continued tracking their trajectories with obsessive precision. The non-gravitational accelerations not only persisted, but intensified. All three main fragments showed acceleration exceeding anything that could plausibly be explained by outgassing. Fragment B is particularly egregious, Dr. McCaley reported during a video conference with NASA's Planetary Defense Coordination Office. Its spectroscopy shows minimal outgassing, mostly carbon monoxide with little dust production. Yet it's accelerating faster than Fragment A, which is producing copious amounts of dust and gas. The physics doesn't work. Outgassing can't explain the trajectory. He ran detailed force balance calculations for the observed spectroscopic brightness and dust production rates. Fragment B should experience non-gravitational acceleration of perhaps 10 to the power of negative 7 m/s². The measured acceleration exceeded 5 times 10 to the power of negative 7 m/s², 5 times too large. To produce such acceleration through rocket effects, the fragment would need to be ejecting material at rates that should make it dramatically brighter than observed. There are only a few possible explanations, Dr. McCaley concluded grimly. Either our understanding of cometary outgassing efficiency is fundamentally wrong, or there's a process occurring that doesn't produce observable ejecta, some kind of reactionless drive, which violates momentum conservation and is physically impossible, or the object is hollow and far less massive than we estimate, making the same momentum change produce larger acceleration. The hollow hypothesis gained surprising traction. If Fragment B were not a solid object, but rather a thin shell surrounding a void, its mass could be 10 or even 100 times less than estimates based on assuming solid density. Lower mass meant the same outgassing could produce proportionally larger acceleration. But how could a hollow object survive interstellar transit? And why would nature produce hollow comets? Dr. Seligman's metastable material hypothesis offered another potential explanation. If the fragments contained pressurized volatiles or exotic ices that released energy through phase transitions rather than simple sublimation, the ejection velocities could be much higher than normal outgassing. High-velocity ejecta meant more momentum per unit mass, potentially explaining the excessive acceleration with less observable outgassing. But when Dr. Seligman submitted his paper for peer review, the referees demanded more detailed calculations and realistic formation scenarios. The paper remained in review limbo, scientifically plausible but too speculative for immediate publication. By mid-December, news of 3I/Atlas's anomalous behavior had leaked sufficiently that mainstream media began reporting the story. Initial coverage was restrained. Articles in Scientific American and Nature News summarizing the unusual composition and fragmentation, carefully avoiding sensationalism. But inevitably, speculation about artificial origins began circulating. The comparison to ʻOumuamua was unavoidable. In 2017 to 2018, that first detected interstellar object had caused enormous controversy when Harvard astronomer Avi Loeb proposed it might be an alien light sail. The suggestion was widely criticized within the astronomical community as premature speculation based on limited data. Most astronomers favored natural explanations involving exotic but plausible cometary physics. Now, 3I/Atlas presented similar puzzles, but with more data and more profound anomalies. Dr. Loeb, predictably, was among the first to suggest the object merited consideration as potentially artificial. We should examine all possibilities, including those that challenge our assumptions about being alone in the universe, he wrote in an essay for Scientific American. When an object exhibits multiple anomalous properties, composition, trajectory, fragmentation geometry, possible radio emissions, the hypothesis of artificial origin deserves scientific investigation, not reflexive dismissal. The response from establishment astronomers was swift and harsh. Dr. Paul Chodas, director of NASA's Center for Near-Earth Object Studies, issued a statement. While 3I/Atlas certainly exhibits unusual properties that we don't yet fully understand, there is no evidence requiring explanations outside known physics. Unusual does not mean artificial. The history of astronomy is filled with puzzling observations that were later explained through natural processes once better data became available. But public fascination with the possibility of alien technology was undeniable. Within days, 3I/Atlas became a trending topic on social media. Amateur astronomers worldwide pointed telescopes at the fragmenting object, many sharing images and data online. Discussion forums filled with speculation ranging from scientifically informed analysis to wild conspiracy theories. The tension between scientific caution and public interest created difficulties for researchers. Grant agencies faced pressure to fund more extensive studies of interstellar objects. Politicians asked NASA administrators whether there was any truth to rumors about alien spacecraft. The scientific community found itself in the uncomfortable position of defending careful, methodical investigation against demands for immediate answers to questions that might not have simple solutions. On January 3, 2020, Dr. Ye's team conducted scheduled Hubble observations of the 3I/Atlas fragments, now receding from the Sun and beginning to fade. To their astonishment, Fragment B, the one with the most anomalous composition and strongest non-gravitational acceleration, had vanished. "It's simply gone," Dr. Ye reported in disbelief. "We pointed Hubble exactly where the trajectory predictions indicated it should be. The pointing is accurate to arcseconds. Fragments A and C are exactly where predicted, but Fragment B is nowhere to be found. It didn't just fade, it disappeared." Frantic follow-up observations with ground-based telescopes confirm Hubble's findings. Fragment B, which had been clearly visible just 2 weeks earlier with magnitude around 22, was now completely undetectable even with the most sensitive instruments. For a comet fragment to fade so rapidly, it would essentially need to cease all outgassing instantly and have no reflective surface whatsoever, both physically impossible for a natural object. Dr. McCaley checked his trajectory calculations obsessively, searching for any errors that might explain a mispredicted position. He found none. Multiple independent groups verified that Fragment B should be exactly where Hubble looked. The inescapable conclusion was that something had happened to alter the fragment trajectory far more dramatically than any previous non-gravitational effects, or the object had somehow ceased to be observable. Could it have disintegrated completely into dust too fine to detect? Dr. Bannister suggested during an emergency video conference. Maybe the fragment was more fragile than we thought and just came apart? But the mathematics didn't support this. For an object to disappear so completely so quickly, it would need to fragment into particles smaller than a few micrometers, essentially vaporize. No known physical process could accomplish this short of vaporization by heating, and the fragment was far too distant from the Sun for thermal effects. Additionally, if the fragment had disintegrated, there should be a residual dust cloud along its orbital path, detectable by its scattered sunlight. Searchers found nothing. The alternative explanation, that Fragment B had somehow accelerated far more violently than previously observed, moving well away from its predicted position, was equally troubling. What force could produce such acceleration? Outgassing couldn't explain it. Fragment B had shown minimal activity. Impact by another body? The probability was infinitesimally small, and there was no debris signature. Gravitational perturbation? There were no massive bodies anywhere near the fragment's trajectory. "I don't have an explanation," Dr. McCaley admitted. "Fragment B should be where we're looking. It's not. Either our understanding of orbital mechanics is wrong, which seems unlikely, or something happened to that fragment that we don't know how to explain." Throughout early 2020, observations of the remaining fragments continued as they faded with increasing distance from the Sun fragment. A behaved relatively normally, following its predicted trajectory and gradually dimming as outgassing decreased. Fragment C remained active longer than expected, still showing a faint coma even at $3 from the Sun, but its trajectory matched calculations. The smaller fragments that had broken off during the main fragmentation event mostly faded from view by mid-January. One exception was a piece-designated fragment D7, which showed erratic brightness fluctuations similar to the pre-fragmentation object. Radio observations by the Arecibo Observatory in Puerto Rico detected intermittent emissions from this fragment as well, though less intense than earlier detections from the intact object. Dr. Margot's team secured additional Green Bank telescope time in February to conduct extensive radio monitoring of all visible fragments. The observations yielded mixed results. Fragment A showed no detectable radio emission above background noise. Fragment C produced weak, sporadic signals that could plausibly be natural maser emission from its coma. Fragment D, 7 continued showing structured narrowband signals near the hydrogen line, but with less regularity than before. If I had to bet, I'd say the radio emissions are natural, Dr. Margot cautiously concluded. There are astrophysical processes, particularly in the boundary regions where cometary gas interacts with the solar wind, that can produce narrowband radio emissions. The hydrogen line frequency is special because that's where natural masers are most likely. But I can't completely rule out other explanations. The signal structure is more complex than typical astrophysical masers. Attempts to detect fragment be continued throughout the spring and summer of 2020. Arrays of ground-based telescopes conducted coordinated searches across wide areas of sky surrounding its predicted position. The Panoramic Survey Telescope and Rapid Response System, PanSTARRS, in Hawaii, which had discovered numerous comets and asteroids, conducted special deep surveys optimized to recover the lost fragment. All efforts failed. Fragment B had simply vanished. By August 2020, most astronomers reluctantly concluded that whatever happened to Fragment B had likely rendered it unrecoverable with current technology. Some speculated it might have been an especially fragile piece that completely disintegrated. Others suggested it might have encountered an undetected small body and been destroyed in a collision. A few couldn't shake the feeling that something more fundamental had occurred, something that current physics didn't accommodate. The scientific papers analyzing 3I/Atlas multiplied throughout 2020 and into 2021. Over 200 peer-reviewed articles examined various aspects of the object, its composition, trajectory, fragmentation, radio emissions, and implications for interstellar object populations. The papers reached wildly different conclusions. One camp, led by established cometary scientists, maintained that 3I/Atlas, while unusual, could be explained through natural processes. Perhaps it formed in a planetary system with very different chemical composition than our own, around a carbon-rich star, or in a region with unusual isotopic ratios. The fragmentation could have been triggered by structural weaknesses introduced during formation or modified by radiation damage during interstellar transit. The excessive non-gravitational acceleration might indicate the fragments were less massive than estimated, possibly porous or fluffy rather than solid. An alternative camp argued that 3I/Atlas represented a genuinely new class of object requiring expansion of existing theoretical frameworks. Perhaps interstellar space contained populations of bodies formed through processes unknown in our solar system, maybe aggregations of molecular cloud material, or ejecta from stellar explosions, or even planetesimals from disrupted planetary systems that had undergone subsequent modification. The object challenged assumptions about what comets could be. A small but vocal minority, including Dr. Loeb and a handful of younger researchers less constrained by career concerns, continued arguing that artificial origin couldn't be dismissed without more definitive evidence. They pointed to the cumulative weight of anomalies, the heterogeneous composition suggesting assembly rather than accretion, the symmetric fragmentation geometry, the excessive non-gravitational forces, the structured radio emissions, and complete disappearance of Fragment B. Individually, each could potentially be explained naturally, they acknowledged, but collectively, the anomalies strain credulity. I'm not claiming 3I/Atlas was an alien spacecraft, Dr. Loeb clarified in numerous interviews. I'm saying the hypothesis deserves investigation rather than reflexive rejection. Science advances by considering all possibilities and allowing data to discriminate among them. The insistence that only natural explanations deserve consideration is philosophical bias, not science. Critics counter that extraordinary claims require extraordinary evidence, and the data from 3I/Atlas, while puzzling, fell far short of proving artificial origin. Every anomaly we've observed has potential natural explanations, even if we haven't determined which explanation is correct, argued Dr. Meach. Invoking aliens is lazy science. It's giving up on finding the real answer because it's difficult. The debate while often heated, reflected genuine scientific uncertainty. 3I/Atlas had revealed that humanity's understanding of interstellar objects was far more limited than previously assumed. Whether that lack of understanding hid mundane natural phenomena or something more profound remained an open question. By 2021, 3I/Atlas had faded beyond the detection limits of even the most powerful telescopes, now more than $6 from the Sun, and receding at its interstellar velocity. The fragments would continue their journey indefinitely, eventually leaving the solar system entirely and returning to the darkness between stars. Barring an improbable future close encounter with another star system, they would remain in interstellar space for millions or billions of years. But the scientific investigation didn't end. Teams continued analyzing archive data, squeezing additional information from every observation. Machine learning algorithms scoured the spectra for subtle features human analysts might have missed. Dynamicists refined trajectory models, searching for any clues about where the object originated. Dr. Alan Jackson at Arizona State University led efforts to trace 3I/Atlas's path backwards through the galaxy. We can calculate its trajectory before entering the solar system based on its observed velocity and direction. The challenge is that even minor uncertainties in velocity translate to huge uncertainties in position over interstellar timescales. We can say it likely originated from somewhere in the general direction of Cassiopeia, but narrowing it down to specific stellar systems is nearly impossible. Still, the exercise revealed interesting possibilities. Several candidate stars lay within 3I/Atlas's plausible origin region, stars that the object might have passed within a few light years of during the past few million years. One particularly intriguing candidate was Gliese 229, a red dwarf star 19 light-years distant. 3I/Atlas's velocity vector, when traced backward and accounting for galactic rotation, passed within about 0.5 light-years of Gliese 229 approximately 5 million years ago. It's just circumstantial, Dr. Jackson cautioned. Gliese 229 is a cool star, and we don't know if it even has a planetary system, let alone whether it could produce objects like 3I/Atlas. But it's tantalizing to identify a specific stellar system that might have been the object's home. The detection of 3I/Atlas also spurred development of improved interstellar object detection capabilities. NASA funded studies for a dedicated Interstellar Object Survey spacecraft that would continuously scan for incoming visitors, providing earlier detection and longer observation windows. The European Space Agency included an interstellar object intercept mission in its long-term planning documents, an ambitious proposal to actually rendezvous with and study the next ʻOumuamua or 3I/Atlas that passed through the inner solar system. The next interstellar object could arrive tomorrow or not for another decade, noted Dr. Michelle Bannister, who served on several of these planning committees. But when it does come, we need to be ready. We can't let another opportunity slip away with so many unanswered questions. As 2025 approached, 6 years after 3I/Atlas's discovery, the object remained one of the most enigmatic in astronomical history. Several fundamental questions remain not just unanswered, but actively debated. What was its composition? The fragments showed such different spectroscopic signatures that their origin from a single parent body seemed almost impossible. How could such heterogeneity arise naturally? Did it form in 3 separate locations and later merge? Or was it assembled from distinct materials? What caused the fragmentation? The symmetric geometry and high separation velocities suggested an energetic, structured breakup unlike typical cometary fragmentation. Was it triggered by internal stresses as subsurface ices vaporize? Or did something more dramatic occur? What produced the excessive non-gravitational accelerations? Even accounting for uncertainties in mass and outgassing efficiency, the trajectory deviations exceeded conventional explanations. Did the object contain exotic materials? Was it hollow? Or were the measurements somehow systematically wrong? Were the radio emissions natural or artificial? The structured signals near the hydrogen line frequency could be explained by natural maser processes, but their complexity remained unusual. Were they just an obscure natural phenomenon, or was something more remarkable occurring? What happened to Fragment B? Of all the mysteries, this remained the most profound. A clearly observable object had simply vanished, defying all predictions and searches. Where did it go? Did it disintegrate completely? Did something alter its trajectory so dramatically that it moved far from its predicted path? The questions had no satisfactory answers. Where did 3I/Atlas originate? The object came from interstellar space. But which stellar system? What were the conditions in that system that produced such an unusual object? These questions might never be answered without interstellar travel capabilities. Despite, or perhaps because of, all the unanswered questions, 3I/Atlas transformed how astronomers thought about interstellar visitors and the diversity of objects populating the galaxy. The assumption that comets from other stellar systems would resemble solar system comets had been shattered. The galaxy clearly contained object types that Earth-based experience had never encountered. The controversy also highlighted tensions within astronomy between conservative empiricism and willingness to consider radical possibilities. The debate about whether 3I/Atlas might be artificial exposed philosophical differences about what constitutes legitimate scientific inquiry and how the field should respond to genuinely anomalous data. For the public, 3I/Atlas became part of humanity's growing awareness that the universe held surprises. That space wasn't just vast and empty, but filled with mysteries waiting to be encountered. Whether those mysteries were profound but natural phenomena or evidence of intelligence beyond Earth remained an open question, one that might only be answered when the next interstellar visitor arrived. And somewhere in the darkness between stars, the fragments of 3I/Atlas continued their eternal journey, carrying secrets that might never be fully understood, enigmas that would tantalize and frustrate scientists for generations. The object that might have been a comet had revealed how much humanity still didn't know about the cosmos, and how,